Hello and welcome to this Chauvin Arnoux webinar. In this webinar we're going to look at low resistance measurement. Hello, my name is Kevin Smith. I'm Business Development and Marketing Manager here at Chauvin Arnoux and I'm going to be your presenter during this webinar. If you'd like to connect with me after the session, you can look me up on LinkedIn. So for those who aren't familiar with Chauvin Arnoux, we were founded in Paris in 1893 by Raphael Chauvin and René Arnoux. Chauvin Arnoux has played a major role in the history of test and measurement. We have a long and prestigious list of inventions, such as the universal tester, the ancestor of the multimeter, and the current clamp. In the 20th century, more than 350 patents and brands were registered by Chauvin Arnoux. Just to give you an idea of some of the numbers involved, we have an annual turnover in the order of 100 million euros in sales revenue per year. We have 10 subsidiaries spread worldwide, of which the UK subsidiary is one of those. We have around 900 employees, 7 production sites, 6 R&D departments worldwide, and we're proud to say that we spend about 11% of our revenues in R&D. So we always ensure that we're creating new and innovative products. So welcome to this webinar. There's a few things we want to go through with you just to make sure that everything runs smoothly. So the first thing is testing 1, 2, 3. Just make sure that you can hear us, that you've got the volume adjusted correctly. And if you do have any problems, it's usually down to some local IT settings, maybe your sound settings, maybe you haven't got your headphones plugged in correctly. In extreme cases, you may have to log off the webinar and log back on again, and that usually cures most problems. So if you just make sure, obviously, you can hear me, everything's running smoothly, and you can see the things on the screen, that's great. So the duration is approximately an hour, something like that, and we also do a live Q&A at the end. So if you've got any questions that you want to talk through, obviously you can type those in the chat box as we go, or you can ask those at the end during the live Q&A. As we said, the chat box or the questions box is available for your questions during the session, and we've got staff on hand to answer those questions during the session, and we will address those at the end. Also, remember to download the presentation handouts. If you have a look on the go-to toolbar, you'll see a handout section, and in there there's a PDF copy of the presentation slides. So to save you writing everything down, we've already provided the slides for you. So just remember before you leave the session to download those a copy of those PDF slides. You will also get a certificate. It'll be sent out to you after the completion of the webinar series. So that's normally within a week or so of us finishing the webinar. You'll normally get your attendance certificate come through by email automatically. The video will also be available on our website, www.cauk.tv. And again, that's usually within a week of the session. We usually put those up on there. But we also have our previous webinars on there, so if you want to check out our previous webinars, please go to www.cauk.tv and take a look. So what are we going to cover today in the webinar? So we've called this webinar low resistance measurement, but it does cover quite a bit of stuff really. It's quite a broad topic. So we're going to start off with an introduction to low resistance measurement. What do we mean by low resistance measurements? We're then going to look at the factors that affect the accuracy of low resistance measurements. We're going to have a look at some of the typical applications that you may come across for testing low resistances and measuring low resistances, and then we'll have a look at what test equipment you might need and the differences between the test equipment to sum up. So with that said, let's get started. In this section, we're going to give you an introduction to low resistance measurement. So let's start off right with the very basics, almost back to your school days. Each material has a unique atomic structure with varying numbers of electrons positioned at varying distances from the nucleus. Therefore, the attractive force which binds the electrons to their parent atom varies greatly from material to material. So as you can imagine, each material has a nucleus in which we've got the protons and neutrons, and then orbiting around there we've got the electrons. So with the electrons, obviously we have different numbers of electrons, different distances, and the attractive force on those is different. So resistance is very much a factor based on the material, as you'll see later in this presentation. The material, the atomic structure of that material makes a big difference to the resistance. So if we look at a material such as copper, it only has a very weak hold on some of its electrons, in this case really one electron in the outer orbits of the atom, and that makes this material, copper, a good electrical conductor. So materials which are good conductors are said to have a low resistance, as they allow electrons and therefore electric current to move easily through them. So if we look at the diagram here, copper atom's actually got 29 electrons, and they are arrayed at different spacings from the nucleus. And you can see that because we've got 29 electrons, we actually have one electron in the sort of outer orbit, the outer electron shell, and that basically makes copper a very good conductor. It's quite easy for that electron to then be transferred from atom to atom to atom, and we get a flow of electrons, which is electricity in that regard. So this is quite a simplified diagram, and I know we could get right into the nuances of it, so please bear with us on that one. But what we're trying to get over is really the fact that resistance is basically a factor of the material and how well those electrons are bound into the structure of the atoms and the material that they're in. And obviously materials that allow electrons to flow easily through them will have a low resistance. Materials that hold on to their electrons quite tightly will have a high resistance. So the resistance of a conductor is dependent on 4 properties. You can remember these properties by using the acronym MALT, M-A-L-T. Now this is something we always talk about really when we start off talking about resistance. So MALT is a good way to remember this, and it's material, area, length and temperature. So if we start off with material, and as I mentioned earlier, each material has a different atomic structure, and therefore each material will have a different resistance. This property is known as its resistivity. So resistivity is really the sort of resistance per unit volume, per cubic meter, I think it is, if you express it that way. Obviously we can express it in different units, but the resistivity is really the term we use for how resistive or not a material is to the flow of electrons. Usually this property has limited effect during testing, as most conductors are made of standard materials such as copper, and these materials are unlikely to change during the test. So obviously when we're making things like cables, we will choose materials that are good conductors, and if we're making insulation, then again we'll choose materials that are good insulators. But obviously during the testing this doesn't really have an effect, because obviously the materials aren't likely to change from test to test to test. So although it's a very important factor on resistance, it's actually not something that we take into account a lot during testing, because it's just a fact. You know, it is copper, it is gold, it is silver, it is, you know, aluminium or whatever, and you know, it is what it is. Now, area or cross-sectional area generally is a better way to look at it. So the cross-sectional area of a conductor, when increased, allows electrons to flow more easily through it. This has the effect of lowering the conductor's resistance. The opposite effect can be observed when a conductor's cross-sectional area is reduced, thus increasing the resistance. The cross-sectional area of a conductor is therefore said to be inversely proportional to its resistance. So if we increase the cross-sectional area, we make the cable fatter, for example, the resistance will go down. If we make the cable thinner, the resistance will go up. And this is a factor that can actually be seen specifically when we're measuring, say, contact resistance of a relay, and you might have a tiny little bit of the contact that's actually touching rather than the whole surface. So what you'll actually find is that's shown by the fact that we've got a reduced cross-sectional area. You know, we should have the whole contact touching. We've only got a tiny spot that's touching. That tiny spot then is reduced cross-sectional area, and that would give us an increase in resistance. So again, these sort of things we can actually use, and we can actually see these properties in the measurements that we carry out, and it actually then helps us to understand what's going on, you know, with certain tests and certain applications. Length. Again, length is an important one. If we increase the length of a conductor, we will increase its resistance. And if we shorten a conductor, its resistance will decrease. Therefore, the length of a conductor and its resistance are said to be directly proportional. If the length of a conductor doubles, then its resistance will also double. If the length is halved, then again the resistance will halve. So this can be used quite often by cable manufacturers potentially to work out the length of a cable, or if they take, during their quality processes, maybe they take a standard meter of a particular cable, and for that standard meter they are expecting a specific resistance measurement. And obviously if that resistance measurement is incorrect, then potentially the material isn't pure, the actual alloys that they've used in the cable aren't correct, or the cross-sectional area may not be correct, or maybe it isn't actually a meter, maybe they've measured it incorrectly. So this is why it's quite important to use these properties, and length again is a very important property. So as we measure over a longer distance, resistance readings will increase, and in a shorter distance they will decrease. And this is why it's quite important when you're actually positioning your test probes, because when you're actually positioning your test probes, you are measuring between those probes. So again, it is important that we're aware of that we know what we're measuring, because if we position the probes in a different position, we will get a different resistance reading just based on the fact that we're measuring a different length of conductor. So the final part of mult is temperature. The temperature of a conductor also affects its resistance. If we increase the temperature of a conductor, we will also increase its resistance. If we lower the temperature of a conductor, we will decrease its resistance. When measuring low resistance values, the conductor temperature is an important thing to know. Many standard resistance values are stated at 20 degrees C, but measured values can be corrected for a known temperature. Measurement currents can also cause conductor temperature to change. So that's an important thing to be aware of, that we can actually, by the way we carry out the test, we can actually affect the temperature. So by using a high measurement current, we could actually even heat up the conductor that we're measuring. So we have to be careful when we're actually carrying out the measurements that we don't affect that, and that if we need to, we can correct for temperatures, and we know that maybe we're doing this in a temperature controlled environment, and we can measure the temperature and actually correct using measurement tables and things like that as well. So it's a very, very important factor, temperature. It's something we don't often think about when we're doing sort of quite basic measurements, but the more you get into it, the more sort of accurate you want to be, the more temperature becomes a factor in your measurements. So when we're measuring low resistances, often things can get a bit jumbled up and people can get a bit confused. So hopefully we can just look into that now in a bit more detail and just discuss it a little. So the subject of low resistance measurement sounds deceptively simple, and this is often where the trap lies. A two-pole voltage detector like our CA 771 has a continuity mode, which beeps when it sees a low resistance. So continuity is often a term that we use, sort of interchangeably for low resistance, but it's not actually the case, because as you can see here, when it beeps, it sees a low resistance, but in this case that just means that it's a value below 100 ohms. So actually it beeps, we think, yep, that's a continuity reading, that's low resistance, but actually that could be up to 100 ohms. And similarly with a multimeter, when we've got a multimeter with a low resistance range, that may even say 0.1 ohms. But are these two things the same? Are we actually getting, when we get a beep on a continuity tester, when we get 0.1 ohms on a multimeter, are these things actually low resistance, and what's the accuracy there? So we will discuss this obviously throughout the rest of the presentation, but it's something just to be aware of, that when we're looking at these things, we need to understand what we're measuring, what we're trying to achieve, and the differences between them. And I think, as we put at the bottom there, are we missing a trick by not accurately measuring low resistances to test installations? And I think there is an argument, the more you look at this, to actually say that in a lot of scenarios it would be, very useful information for us to actually carry out true low resistance measurements, because we can actually check connections, we can actually see deterioration, we can actually see corrosion and all these things in true low resistance measurements, where in many cases we might just go, yep, quick beep with a multimeter and say, yeah, that's fine. And actually if we checked it with a proper low resistance ohm meter or micro ohm meter, there might be a lot more data there that we're actually missing. So I think sometimes by just conflating all these things together, we actually do really miss a trick. So as with many things, the methods used for measurement depends on what we're trying to find out and to what level of accuracy. The term continuity is often used in the context of low resistance measurement, but it only really signifies a closed circuit between 2 points, i.e. that they're not open circuit. So it's great if we're looking for breaks in a wire, or we're looking to see which end of one plug's connected to which pin on another plug or something like that. We're doing a continuity measurement, but really it doesn't tell you a lot more than that. It certainly doesn't tell you about the quality of connections and, deterioration or frayed cables or anything like that. It is just literally telling you that, between the 2 points there is an electrical connection, there is continuity. True low resistance measurements are generally accepted as those resistances below 1 ohm. And we would expect an actual measured value in ohms to be displayed on the meter. So when we're talking about low resistance measurement, we can really rule out continuity measurements, because although sometimes we use the term continuity, as we said, this could be anything under 100 ohms in the case of this tester. So really, when we're talking about low resistances, we're talking about things that are generally below an ohm, often way, way, way smaller than that. An ohm is actually quite a big value when you look at, micro ohms, when we're actually using micro ohm meters. So it is important to understand the context. What are we trying to measure? What are we trying to prove? Like I say, if we're just trying to trace a cable by beeping both ends of a connector, yeah, perfectly acceptable to use a continuity checker with a beep function on it. But when we actually want to measure the quality of connections, maybe on a buzz bar, or, check that a relay is working properly, we really need to get right down into those resistances, and that's where true low resistance measurement comes in. So we've got various options for low resistance measurement, and in many cases we may just use a simple 2-wire resistance measurement. So simple ohm meters use the 2-wire measurement technique. So in this, a constant or known current is passed through the resistance under test, and then the meter measures the voltage drop between its terminals. From this information, Ohm's law is used to calculate and display the resistance. So if you look at the diagram on the right hand side there, you can actually see what's going on. So we've got our insulation continuity tester there, the 6524, and what we're doing, we're carrying out a 2-wire measurement. So both leads are used for effectively voltage and current. So we pass a known current through the load, through the resistance, and we measure the volts drop across the 2 terminals. And because we've got current and we've got voltage, we can work out what the resistance is using Ohm's law, and that gives us our measured value. Now, there are some drawbacks with this, and as we've said in the slide here, this method is affected by lead and contact resistance, and also many other effects that limit the accuracy possible. So again, when we start looking at this, we've actually got, because we're measuring the volts drop between the measurement terminals effectively inside the tester, the lead resistance and any contact resistance is included in the measurements. Now we can zero lead resistance, we can touch the leads together and we can zero those out, so we can sort of account for that really. But again, contact resistance is key on this as well, because where we actually make the connections between the probes to the material under test, we actually need to have really good, really clean contacts in there. And generally with this as well, these measurements are usually carried out at quite low current, so sort of 20 milliamps, 200 milliamps, those sort of levels. So because of the method that's used, and things like lead resistance and contact resistance and all the other factors we'll talk about later in this webinar, there is a limit to the accuracy that you're going to achieve with a 2-wire measurement. So if we just look at typical 2-wire test instruments we've got on here, we've obviously got on the left hand side there the 771, and we talked about that really, that's accurate down to below 100 ohms, somewhere in that category. And we said really that probably wasn't even a resistance measurement, it's more of a continuity measurement. Now, one that sometimes people get confused with, and we get questions about this, is why can't I use my multimeter? You know, it's got an ohms range. Why can't I use my multimeter for measuring low resistances? And you can, but down to about 0.1 of an ohm. That's about the limit of the accuracy with a multimeter. Is about down to 0.1 of an ohm. So we generally can't really get low enough to actually learn a great deal about the connections. You know, we can get low, we can see that it's a low value, but it's not really enough to actually give us the level of information we need to say that a connection is tight or something like that we would do with a micro-ohm meter. Now, where quite often there's a bit of a crossover is when we get to our sort of electrical installation testing, BS 7671 and other standards like that. We get into this region where generally to carry out those sort of testing, the specified, sort of measurement range is really down to 0.01 ohms. So we're reading, down to 0.01 ohms in that sort of region is when we're actually doing things like maybe our R1, R2 test or R2 tests and stuff like that, or checking our main potential bonding conductors maybe. So you could be using a multifunction tester like our CA 6117, or maybe a standalone insulation continuity tester like the 6524 there. Both of these employ a 2-wire measurement, and both of them will only really get down to that 0.01 of an ohm. And actually, this is where I think there's a bit of a gap. There's a bit of a sort of a gap in the market really. Is those sort of testers, because when you start to look at the accuracy at the very low values there with the 2-wire test, they are quite limited in their accuracy, and they are quite limited in what the information you're actually being displayed, the information you're actually being told, because it is a 2-wire test, and I'm not just saying this is anything to do with Chauvin Arnoux products. This is just in general. There is actually a general discussion is are these types of instruments really going into the level of continuity that actually would be useful for electrical installation, inspection and testing. Because really, if we could get to another level of accuracy, we could actually identify more, poor connections, circuit breakers that were starting to wear out, poor bonding connections, all these sorts of things. We could actually start and identify a lot more problems with electrical installation. Even things like ring main tests, we could actually do a hell of a lot better job on doing a ring main test if we had a tester with that extra degree of accuracy, because it would actually tell us a lot more about what was going on with the installation. It would give us a lot more confidence in that environment. So there is sort of a debate, and I'm just really, sparking this debate because, there's a standard, it's there, and it says that things are done in a certain way. But when you actually look at using these sort of 2-wire tests, and this is industry standard for doing those tests, I think, as I said before, I think maybe we are missing a trick by not actually doing these tests in a bit more detail and actually being able to get the additional information that we could gain by using a more accurate method. So 2-wire resistance testing, it's there. Be aware of the level of accuracy, be aware of the level of ranges you can get to. And as we said, this is sort of industry standard. And hopefully with these, you can see why we can't just use a normal multimeter now to do our sort of 17th edition, 18th edition BS 7671 testing. Because we are, required to get down to that 0.01 ohms type range. But again, I think we would benefit with doing those tests to go that little step further, and I think that's something that maybe we can discuss a bit more later on in the live Q&A. Now, what's the next step? Well, if we want to increase the accuracy, generally in the industry, there are other methods, but generally in the industry, we've pretty much standardized on this 4-wire, what we call Kelvin test method. And this is a really clever trick. It's sort of when you understand it, you think, oh, actually, I really like the way that's been done. So what we do is we actually, rather than using 2 wires, we actually split our measurements up. We have 2 measurement circuits effectively, or two parts of the test circuit. So what we have is we have our constant known current circuit. So when you look on the tester, we actually have our current terminals, C1 and C2. And what they do is they pass a current through the resistance under test. So we pass that current through the resistance under test. And then we use two potential terminals, P1 and P2, to measure the volts drop. So the good thing is we've got the current circuit. Now that current circuit is separate, so we could be passing a big chunky current through that circuit, and that can be measured. So again, by passing the current and measuring what the current is, things like contact resistance don't really matter because we know what current is traveling through there, and we're measuring it separately. And then because the voltage terminals, we can actually then use a high impedance voltage meter effectively to measure the volts drop. So we can use a very accurate high impedance voltage meter, and that will then again not be affected by things like contact resistance because it's a very high impedance measurement circuit. And we can accurately then measure the voltage, and again same thing, bit of Ohm's law, and we get the resistance. But by separating the current path, where we can pass this current through, and the potential measurement, the sensing part of the circuit, by separating those two up, we can increase the level of accuracy that we're going to get. And this is the standard sort of 4-wire or Kelvin type setup that we use, and this is standard on all, you know, really accurate low resistance meters. So you can see, again, by separating the current injection and the voltage sensing circuits, many of the drawbacks of a 2-wire system, such as the impact of contact resistance and test lead resistance, can be avoided. And this is why the 4-wire method is the standard way to measure low resistance values where accuracy is required. So we looked at, in a couple of slides ago, we actually had a look at the sort of levels of measurements that you could get out of, you know, the sort of standard 2-wire type tests. So we were talking about maybe getting down to 0.1 of an ohm, or maybe 0.01 of an ohm. That was the sort of level we were talking about, really is where you'll get to with a 2-wire test. This is a different league, as you can see. When we get into 4-wire measurement with the micro-ohmmeters, we are talking, you know, where we start off with our, you know, for want of a better term, least accurate, you know, most popular, but least accurate micro-ohmmeter. This will actually measure down to 5 micro-ohms. So that's 5 millionths of an ohm. So when we were talking about 0.1 or 0.01, this is 0.0000005 of an ohm. So again, we're talking really, really small values, and you can see it's just a total step change in the level of accuracy that can be achieved. And by doing that, that opens up so many more, you know, options for us to be able to actually, you know, get useful information by doing these low resistance measurements. If we then step up one to our 6255, we're then down to 1 micro-ohm. So we can actually measure down to a single micro-ohm, you know, hence the name, micro-ohm meter. So we're actually measuring down to a micro-ohm. And if we go up another step again to our 6292, this can actually measure to 0.1 of a micro-ohm. So that's 0.1 of a millionth of an ohm, or 100 nano-ohms if you want to put it that way around. So we're really, really, really getting into those low resistance measurements. So you can see the difference when we're actually talking about, you know, low resistance measurement. A lot of times people, you know, anything, you know, we're saying anything under 100 ohms, it's a low resistance. These are truly low resistance measurements, and this is the sort of category that we're getting into when we get into proper micro-ohmmeters and 4-wire measurement. And it does just show you the difference of the information that you could get if you actually stepped into this type of measurement. So when we're carrying out these measurements, obviously we need to make these connections, and the normal way that we'd actually make these connections is by using 4 separate clamps or 4 separate probes. You would have obviously 2 current probes, C1 and C2, and 2 potential probes, P1 and P2. Now, when we connect these, we said that we pass the current through the circuit. So that goes through C1 and C2. So we would position those outside of the sensing contacts, of the potential contacts. So we connect those on C1, C2 on the outside, and then inside of that, we would then connect the sensing circuit, the potential circuit P1, P2, inside of that. So the current travels round, we're then measuring inside of that, and then basically that's where we take the measurement. Now, when we are measuring inside, just be aware, we talked about the length, we talked about actually the, the measurement positioning of the probes. When you're actually positioning P1 and P2, that's where it's going to measure in between. So if you're worried about the length, say you were trying to measure the resistance of a cable, it's the distance between P1 and P2 that you're actually measuring the resistance of, not the position of C1 or C2. So you might put C1 or C2 a metre apart, put P1 and P2 in the middle and think you're measuring a metre, you're not. So measure, put your C1, C2 either side, and then the distance between P1 and P2, that is the actual resistance you're measuring. So where you're clipping those on does actually really matter when you're doing this, so it's really important. So good practice or best practice is to use 4 separate connections, and then we can position those and get some really good contacts. But that isn't always possible. When you're measuring things, you might only have access to a particular terminal or screw head or some sort of test point that you're actually measuring at. So there is other options, and one we've got on the right hand side of the slide here is what we call Kelvin Clamps. And these are quite clever crocodile clips actually, because what you've got is you've got a different wire going to each jaw. So one jaw will have the current connection and the other jaw will have the potential connection. So what you've actually got with 2 croc clips there is 4 connections. And because they're actually sort of opposed to each other, if you get me, when you clip them on, it doesn't really affect the measurement accuracy from that side of things because they are separated apart when you connect these things up. So you've actually got both connections in each crocodile clip. So you'll have a potential and a current one and a potential and a current one in those croc clips. And when you make those connections, you're actually getting your 4 contacts, but you're only using 2 clips to do it. And it means it's quite easy to actually get to the actual contact points to take your measurement. So Kelvin clamps, or sort of the 2-wire type clamp. Sometimes people get confused because they look at them and just think it's a normal croc clip, but actually you've got 2 wires going in there and each jaw is wired up separately. Now we can also get these Kelvin type probes, and there's a lot of different versions of these, different sizes, different shapes. But what you can see here is the fundamental part is, again, that you've actually got 2 probes in the end, and these are generally spring-loaded probes, so they sort of, when you push them on, they'll fit around any sort of surface imperfections or any movement of your hand position. But one thing to note really carefully is you'll see on these ones of ours where you've actually got a little red dot, and that red dot indicates the voltage connection, the potential connection. So the outside one, the one that hasn't got the dot, is the current connection, and the one that's got the dot is the potential connection. So as you can see on the left hand side there, when we're actually connecting these probes up, what we do is we turn the red dots onto the inside so that the red dot is actually inside. So your potential connection is on the inside, your current connection is on the outside. So that's how we achieve the sort of, the correct positioning of these probes. So you can see where it is, you can position it when you're carrying out your measurements, and that obviously ensures that you get the best and most accurate measurements by using these probes. So these are great if you want to make contacts onto some quite small items where, getting big chunky crocodile clips on or something like that, or certainly, 2 or 4 sets of crocodile clips is going to be difficult. So in this case, these probes are very good. We do offer a range of different types of probes that you can use, but in this case, obviously, just be aware that we do note where the potential and the current probes are and position them accordingly. So it's quite an interesting one. That one's something maybe that most people aren't aware of. So now we're going to take a look at the factors that affect the accuracy of low resistance measurement. So the first factor we're going to have a look at is the actual accuracy of the test instrument itself. You must always select a test instrument that is suitable for the required measurement accuracy. A low accuracy tester will never be suitable if you need a high level of accuracy in your results. And a high accuracy tester will likely be too large and expensive if only a low level of accuracy is required. So it may sound like common sense, but sometimes people overkill what they want. They think, well, we need a massive level of accuracy, when actually really all they're going to do is drive themselves up the wall, because they've got a huge great tester, it's really accurate, in which case it's really sensitive to temperature fluctuations and really sensitive to all sorts of test conditions. When actually, if all you wanted to do was actually measure to a reasonably low tolerance, you may have got away with a simple 2-pole tester, when really actually, you've bought a 4-wire tester and you're driving yourself mad trying to get it to work in an on-site environment maybe. But the other way round, if you're actually trying to measure, you're trying to look for, say, contact resistance on a contactor, but you're actually using a 2-pole tester, it's only accurate to point something of an ohm, you're never going to see anything in the results. The results are just going to be up and down. You're within, the accuracy of it is sort of not there enough for you to see what you're doing, and it's, you just end up chasing your tail. So always think backwards. Think, what's the outcome that I want? So the first thing to think about, what's the outcome that I want? What am I trying to achieve? What level of accuracy do I need to achieve? And then work backwards to your test and measurement solution from there. Because, it's like anything, it's just fitness for purpose. You get the right device for the right level of accuracy, you're there, and it'll work, it'll do what you want. But sometimes, people try and penny pinch and think, oh, I can get away with a cheap one, it'll be okay. And actually it just drives them up the wall. It's a false economy. Otherwise, sometimes people will get mad and try and get, the best, most accurate solution, when actually all they need is, a simple solution. So again, it may seem common sense to say it, but when you're selecting these instruments, always just think about, what am I trying to achieve? Pick the right instrument for the job, and everything will work a lot smoother. Operating conditions. Now, this covers a hell of a lot of things, operating conditions. So to achieve accurate and repeatable low resistance measurements, it will be key that you're aware of and can control the operating conditions of the test environment and the item under test. Check the manufacturer's guidance. So this is important, that again, it'd be in the manuals for all of our products. If you have a look in there, it will give you the operating conditions, the temperature range, the humidities, the altitudes, all sorts of things will be in there. The operating range of those pieces of equipment. And you need to match, again, the instrument that you're using to the environment. So if it says it must be used within quite a strict temperature environment, you need to make sure that you're actually able to provide that you're not out on top of a windy hillside when you've got to achieve laboratory type temperature control to actually get that level of measurement. So we do need to think about the operating conditions. Now, temperature is the most important factor, and a temperature control environment is ideal for these tests. Temperature is a really important thing when we're looking at operating conditions, but there is other things like moisture and humidity and all this sort of stuff, but temperature is very important. And even things like drafts or, wind and stuff like that can affect the temperature of your sample, the thing that you're testing, and actually cause problems when you're trying to, do really, really, really accurate measurements, or if you're out in the sun, for example, or, the desert maybe. So it is really important to try and control your environment, to know the operating conditions and understand the limitations of the type of accuracy you're trying to get. If you're trying to get laboratory level, resistance standard accuracy up on the top of a mountain somewhere, it's not going to work. So you do need to understand the operating conditions, do what you can to control that. And again, we will talk about other factors that affect these things, and and there are things that you can do to control. For example, we're talking here about the temperature, but electromagnetic interference is another example where you need to try and control your test environment. So it is important to think about that up front, because it will have a huge effect on the level of accuracy that you're actually able to achieve. Lead and contact resistance. So the resistance of a test leads can often be larger than that of the item under test. And in many cases it is, you've got a very low resistance you're trying to measure and you've got quite high resistance test leads. A poor contact between test connections and the item under test can also lead to increased or unstable measurement. So yeah, it's really important that you've got a good, reliable connection. Ideally, not something you need to hold with your hand. Yes, we talked about Kelvin probes and things like that, but obviously that is prone to you holding still while you're carrying out the measurements. And in a lot of places, they do actually use specific test jigs where the things are actually clamped in and specific test pins are positioned onto the work, the workpiece, so that you can actually get these measurements without, being able to wobble your hands around and all these sort of things. Now, there is options. Zeroing lead resistance and cleaning connection points are always good practice where possible. This is specifically true for 2-wire measurements, but again, 4-wire measurements, it is, again, still good practice where we can to have good, clean, reliable test contacts. So the use of a 4-wire test method can greatly reduce these effects, but even the 4-wire configuration, care must be taken to ensure a good and stable connection. That word stable is very important. You don't want it to be moving about, or you don't want it to be changing during the measurement. Voltage connections must be placed at the point of test. We talked about this, so the voltage connection is where you're actually measuring, and these should be inside the current connections. The connection should not be moved during the test. So again, very important to think about lead resistance, think about contact resistance, but also, nice clean surfaces, nice clean stable test connections. Less important when we get onto the 4-wire measurement, but actually for 2-wire measurement, it's vitally important. Thermocouple effects. Sometimes this is called thermal EMFs. So you may be aware of thermocouples. Thermocouples are a device that's quite often used for measuring temperature. And a thermocouple is a very simple device. It's just really 2 dissimilar metals connected together, and under a certain temperature, they generate an electromotive force, a voltage. And by measuring the voltage, we can actually measure the temperature. So you've probably come across the term thermocouple many times with temperature measurement, but actually thermocouple effects can cause problems when we're doing low resistance measurement. So in any system where there's mixed metals, such as nickel plating on copper, for example, so even on your test leads, if you've got a nickel plating on the outside of your copper probe, for example, or crocodile clips, this junction forms a thermocouple, and when exposed to heat, an EMF, which is basically a DC voltage, will be generated. This EMF will affect the voltage sensed by the ohm meter. Reversing the polarity and averaging the results can cancel out this effect. So because we've got a DC voltage is being created, what it will do, it'll effectively add to the voltage in one direction and subtract from the voltage in the other direction. Now, if we're sensing the voltage to measure the resistance, if we measure with positive and negative one way round, we measure one polarity, and then we automatically switch round and measure the polarity in the opposite direction, what that does is it gives us 2 readings. And in the first reading, maybe the EMF will add to our reading, and in the second reading, it will take away. So if we actually average those 2 values, effectively what's in the middle is the true value with the EMF due to the thermocouple effect cancelled out. So many testers, many micro-ohmmeters hours include this automatic reversing function. So they will measure one way, they'll measure the other way, and by doing that we actually get the average value. Where you've got to be careful with this is when we're measuring inductive loads. So if we're actually measuring, say, the windings of a motor or windings of a transformer, these are inductors. So what we do is when we actually charge them up in one direction, it takes time for it to charge up to actually get up to that level of voltage, because the energy's been built up within the magnetic field. Also, when you switch over, you will discharge that voltage. So you can get a back EMF, you can get a discharge voltage. which can potentially, if it's not correctly designed, damage the equipment under test. But then also it takes time to build up in the opposite direction. So when you look at some of the testers, they have actually got these functions built in to actually allow for inductive measurement, so it actually gives more time and it's able to dissipate the electric field. And sometimes, measurements are even taken at, sort of different frequencies and all sorts of things. So it is something to be aware of, that if you are carrying out these tests in, inductive loads like, say, motor windings, generators, things like that, just be aware that the reverse functions, which are great for normal resistance to get rid of the thermocouple effects, can cause other issues. So just be aware that you've read the manufacturer instructions and you understand exactly what mode to set it up on for what you're testing. So that's thermocouple effects. Now, electromagnetic interference, or EMI. So often testing may be carried out in the presence of large magnetic fields. Well, that's no surprise, as electricians generally we operate in the presence of large magnetic fields. So that could be cables, with currents travelling down them. We've got a large magnetic field travelling around them. It could be transformers, it could be motors, it could be all sorts of things where we've got these large magnetic fields. And if these fields are changing, so in the case of AC, or if the test leads or the item under test is moving, so even if we've got a static electromagnetic field, if we then move the device under test or move the test leads, it's still the same effect. We can still induce unwanted voltages into the test circuit, and that can cause errors. High frequency electromagnetic interference, such as radio waves, can also cause problems. So we've got the sort of general, what we call maybe low frequency, but the general sort of, mains frequencies generating these electromagnetic fields. We've got electromagnetic fields that are involved by us actually moving the test piece or moving the test leads within a magnetic field. But then we've also got these high frequencies that are all over the place. This could be a Wi-Fi, it could be a TV signal, a radio signal, another transmitter, or anything like that that's present. All of these things can induce voltages into the test circuit, and again can cause problems. Now, luckily with most test equipment, they're quite well screened, quite well shielded against these things, but they can cause issues. So where possible, testing should be performed in a location with low levels of electromagnetic interference. So that's something to think about when we're actually carrying out the testing. Do we need to do it right by the side of the mains transformer, or could we do this at another location where it's not going to be as critical? Test leads should be kept short, because obviously long test leads and also big loops of test leads act like an antenna, and they'll actually sort of, attract these currents, these induced voltages and currents more. And the use of screened leads will also help in extreme cases. So again, we can get screened cables if there's nothing else we can do. We could use screened cables, and again, that will minimize these effects. Test leads and the item under test should be kept still during the test to avoid movement-induced voltages. So again, position everything where we can and try not to move it if we can during the testing, and that will also help to avoid electromagnetic interference. Now let's take a look at some typical applications that require low resistance measurement. The first one we're going to talk about here is busbars and electrical connections. Low resistance measurements are key to the construction, commissioning and maintenance of any high current electrical installations. By taking measurements on a new installation, we ensure correct construction and establish a benchmark against which future measurements can be compared. So you can imagine, if we're constructing this busbar system, we can actually take resistance measurements to make sure that we've actually got very good copper to copper, connections between the two. Because if you look at these under a microscope, there isn't necessarily a flat surface where these things mate. We might have a burr, we might have some contamination, some, dirt or whatever trapped within the connection. You're not necessarily going to see that straight away, but if we actually carry out measurements, we can actually compare, you know, from one buzz bar to the next, or we can actually have specific values that we know that we need to achieve to make sure, you know, that we're actually getting a good electrical connection. And this is also, you know, this is good during the construction process to make sure we've actually, you know, got good construction. We've actually, you know, made these connections properly. We've used good workmanship and good standards. But also that those values can then be used down the line when we come to do maintenance, you know, to see if these things have increased. And it's very typical that if we have got bad connections, that's going to be a hotspot. That's, you know, if that's a bad connection, it's carrying that current through a smaller cross-sectional area. We can actually end up creating, you know, hotspots. That'll be a failure point. It'll be something where it gets hotter, which could cause thermal cycling, which could mean your nuts, your connections are more likely to come undone and all sorts of things. So actually, when we're creating these connections, it's good practice. In fact, it's pretty much essential that we actually do check these joints with something like a micro-ohmmeter to make sure that we have actually got those correct in the first place. And then if we're doing some fault finding or maintenance later on, again, we can return to that and actually identify problems with the installation by, again, comparing to those values that we achieved in the first place. Now, a similar application here is switchgear contacts and relays. So any electrical switching contacts are prone to wear, corrosion, and contamination. So when we're talking about switching contacts, you know, the bits within the switch, the circuit breaker, the relay that actually touch together to make a good connection temporarily to carry that current. And if they do pit or arcing burns them, or they get contaminated with soot or, you know, copper buildup, dust buildup, or anything like that, again, we can see that with a micro-ohmmeter. We can see that by doing a low resistance reading. So by reading across those contacts, we can actually see that we've got, you know, potentially any of these issues are present. So low resistance measurements can identify poor connections in switching components, and this is also a sign that overheating may be occurring too. And as we talked about with the buzz bars, sometimes where you do get poor connections, that's when you're going to start to get heating, and that's when you're going to start to get, you know, problems, fires, all sorts of things in there. So again, by checking our contacts, by making sure these things are set up correctly in the first place, and then monitoring them over time, we can identify, you know, we can preempt any failures before it gets too serious. So, motors and generator windings. It's hard to measure such rotating machines when in use, especially the temperature measurements of individual windings. So you imagine, how do we measure the temperature of an individual winding within this motor while it's being used? Almost impossible. So low resistance measurements can identify poor connections. So we can take the motor apart. We can actually go on the commutator or wherever at the end of the connections and actually check that we've got good connections. You know, we might have a dodgy winding that's gone open circuit, or maybe even gone short circuit to a neighbouring winding. So we can check those as well. But also we can look at heating effects, and this is quite a sort of clever application, really. So what they do is they actually take winding measurements as the motor cools. So we can take a cold measurement at the start. We can then run the motor for a period of time, take it apart, and as it cools, we take temperature measurements and resistance measurements, and we can plot a curve. What we can do with that curve then is we can sort of backtrack up the curve to actually see what the resistance would have been and what the temperature would have been at certain conditions. So we can see where, for example, one winding is actually getting a lot hotter than others. We can actually identify that by plotting these curves. And this is something that's, you know, it is a typical application where micro-ohmmeters are used for actually, you know, doing these sort of checks on large motors and generators. Cable and component manufacture. So if we've got a factory where we're making, you know, cables, or maybe components where we're making resistors, or, you know, all sorts of things, relays, heating elements, maybe for kettles or toasters or something like that. Manufacturers use low resistance measurement as part of their quality assurance procedures. The measurements often take place in a temperature controlled quality assurance lab to ensure consistent measurement. So Generally, these things aren't really done on the shop floor. You know, they'll take a sample away, they'll take it into the laboratory, known conditions, you know, temperature controlled, and generally special measurement jigs are used to make the test connections and reduce errors. So they'll have a special jig set up with the 4-wire measurement set up, you know, the current probes, the potential probes all set up in the jig. They'll position the sample into that, you know, clamp it down and take the measurements, and with that they can actually control the environment, control the measurements, reduce any errors as much as possible, and get, you know, a consistent measurement. So it's quite a common application for these sort of manufacturers to use micro-ohmmeters as part of their quality assurance procedures for their manufacturing processes. Aviation manufacture and maintenance. So for improved protection against lightning strikes and electromagnetic interference, aeroplanes are constructed with all parts electrically bonded together into a big Faraday cage. So yeah, so within the construction of an aeroplane, either the parts are electrically bonded, so they're actually continuous, you know, they've used conductive adhesives or whatever it is, they're actually bonded together, or there's physical, you know, bonding straps, cables, joining everything together. So it is all one big Faraday cage. So if they are in a thunderstorm and there is local lightning strikes, everything goes to the same potential and it just passes through without damaging anything within the aircraft. So during manufacture and maintenance, low resistance measurement are used to confirm and monitor these bonded joints. So again, we'll actually go through and measure, you know, that all these parts are actually connected to everything else. And this is something that's done as part of the production process, obviously, but also it can be done during maintenance. So if they have to change a component, then obviously they need to confirm that that component's been, you know, reconnected correctly. Now, there are a few other applications that are just worth mentioning. So things like wind turbines, again, generally for lightning protection, they are all bonded together. So effectively the blades on the wind turbine are actually connected to the body and connected down to earth. So these things need checking. These things need measuring, and generally it will be a low resistance ohmmeter that's actually used for that. Lightning protection systems in buildings. So again, we may have these big, you know, copper straps coming down the outside of a building, and we may have connections there, and they go to earth spikes and join off to different connections, and there's bolts and brackets and all sorts of stuff. Again, how do we ensure that they're correctly connected? We can use a low resistance ohmmeter to do that. Coating and plating manufacture, or coating and plating, you know, processes within manufacturing. So because of the accuracy that we are able to get down to, we can actually use these to measure, you know, the thickness of coatings that are actually applied to materials, and the fact that, you know, the plating is actually correct, it's there, it's the right material and stuff. So they are used within those environments to check these processes. Railways. Again, in railways, we have a lot of big chunky pieces of metal that need to be joined together, whether that's the rail lines on a third rail system, or it could be point systems, it could be overhead lines, it could be earthing systems within there. So yeah, there's a lot of use of micro-ohmmeters within the railway industry. Automotive manufacturer, yeah, again, there's a lot of applications within automotive manufacture where micro-ohmmeters are used. So this could be wiring looms, it could be connections, particularly with EV now, you know, where we've got these sort of big chunky DC cables for the batteries. Again, making sure the terminations on those are correct is very, very important. But a lot of times they're used actually to check things like spot welds, to make sure that a spot weld is actually made, you know, a good connection. So you can actually even use micro-ohmmeters, you know, in welding applications as well. And there are many, many more. You know, we can't cover every application in here, and really there isn't a definitive list of all the applications. But I think one of the things that I'd just like to challenge you a little bit to do, you know, today is just have a think of your own electrical experience, your own environment, and actually you will see areas where these could be used to improve, you know, maybe your fault finding, maybe the reliability, maybe actually preemptive maintenance. I certainly believe there's a lot more application for these in the normal sort of 18th edition BS7671 type installations. You know, particularly when we're looking at bonding connections and bonding conductors and stuff like this. I think actually having a greater degree of accuracy on those measurements would be very useful. I think the sort of the limit of the accuracy of the testers that we are using is, you know, it's on the edge of what we need, but I don't think it actually goes that extra step. And I also think from a fault finding point of view, you know, we could actually diagnose quite a few more things a lot earlier by using low resistance measurements. So that's just a little bit of a challenge to you to think of more applications that you could actually use these for. And actually, I think they are a useful tool that a lot of people aren't really aware of and aren't really aware of the benefits of. So hence why we're doing this session, really to get people to think a bit more about how they could use these to improve their electrical practice. And the last section we're going to cover today is to have a look at the test equipment that you need to actually carry out low resistance measurement. So we start off here. I've just included our insulation and continuity tester. This is the 6526. We do have a range of these, all from the 6522 all the way through, just depending on different ranges and all sorts of things. But I'm just showing you the 6526, which is the sort of top of the range one here. These are great little products. As we discussed, they're a simple 2-wire measurement, but really they do, they do a really good job, and they're a really useful addition to most electricians' toolboxes. It's a combined insulation and continuity tester, so you can do insulation resistance measurements and your sort of 2-wire resistance measurements. So this would be the sort of thing that would be suitable for measuring under the 18th edition BS 7671 down to those sort of levels, 0.01 of an ohm type readings. So again, really great, portable, rugged, reliable, all these things I can say about it, but very easy to use. So it's a 2-wire measurement method. It uses either 20 milliamp test current or a 200 milliamp test current. It's light and portable, so it just fits in your hand. It's hard to see, the scale of it in here, but it's sort of, multimeter sort of size. It's got the option to 0 and 0, so you can actually zero off your test lead resistance. And it has actually got a memory in here, so you can actually record the results that you've obtained in there. There is also, which is very, very useful, a remote probe option for it as well. I know a lot of people like those when you do measurements, so you don't have to, sort of have balancing 3 hands and holding something in your mouth at the same time. You can actually use the remote probe to do the tests. So for those of you who are in the market for just a simple sort of, either a backup to your multifunction tester or something that's quick and easy to use if you're just wanting to do some basic, low resistance measurement or some insulation resistance tests, just have a look at these, because they are a cracking little range of sort of insulation continuity multimeters. So we've just included that because this is really the starting point in the range. But as we said, these are low resistance ohm meters, but we're not into the true 4-wire measurement. So now moving into our entry level, shall we say, 4-wire micro-ohm meters. This is the CA6240. This is by far one of the most popular 4-wire micro-ohm meters. We sell a lot of these. There's a lot of these in circulation all over the place, and I think these are, they're probably the most popular of our micro-ohm meters, and they really do, most things that everybody would want, really. So, if you are looking to get started, this really is the product that you want to be looking at. So it's 4-wire measurement, so it's proper 4-wire measurement, as you can see on there. You've got your current and potential terminals. It does the current reversal, so when we're talking about the thermocouple effects, we've got the current reversal that we can do in there as well, which is good. It's got a test current up to 10 amps. So generally a lot of the tests are carried out at lower than that, but to get up to the highest accuracy range, that would be a 10 amp test. Really easy to use. You can see on here it's just a turning knob to select the range, and then basically a start-stop button to do the tests. So really simple. But it's also got some great features like the automatic on the fly or manual recording mode. So again, you can connect it up, set it going, and it will just automatically, whenever you make a connection, it will automatically store that result, and you can save your results and then download them to the software afterwards. So again, it's got just enough in there, by way of memory storage that just allows you to not have to think about it, to not have to have a piece of paper there following around with you writing everything down. You can just do those quick tests and then they'll just be recorded one after another in sequence in the memory. It is battery powered, so you connect it up, charge it up, and then it is battery powered. And you can take it anywhere really. They're very rugged. They're designed in a pelly case, so the construction of them is very rugged for use on site. And actually they're deceptively small. When you look at it on here, it looks quite big, but actually they're probably a lot smaller than you'd actually think when you do see them in real life, and really portable. And I know they're just massively popular with our customers that want micro ohm meters. So yeah, can't recommend these highly enough, the 6240. Going up a step to its bigger brother, we're on to the 6255. Again, a 4-wire micro ohm meter. And this has got a few extra improvements above and beyond what you'd expect off the 6240. So it is 4-wire measurement. It's got increased levels of accuracy. So we're actually able to measure down to a micro ohm, so the actual levels of accuracy are improved. It still goes test currents up to 10 amps, so it's still a 10 amp micro ohm meter technically. It's got methods on here, so it's got an actual external probe for temperature compensation. So that gives you the extra accuracy. It's also got a large test memory, so we can store up to 1500 tests in here. And it's actually got an inductive test mode. So when we were talking about being able to measure inductive loads, like motor windings and transformer windings, things like that, we said it can be problematic with reversing modes. This has actually got a specific mode on it designed specifically for testing those type of items. So if you're thinking of testing a lot of motors or generator windings, things like that, again, this is probably worth looking at because it's just got those extra functions on there and that increased accuracy. So still a very popular product, and again, just gives you a few extra features really above the 6240, but again, great product. Moving up to the big boy now. This is the top of the range micro ohm meter that we've got. This is the 6292, and this is a 200 amp micro ohm meter. So this will actually, we're going from 10 amps up to 200 amps in this case, and this is really, this is a sort of production level type tester, which will actually do, I think it'll actually do 100 amp tests indefinitely. There's no sort of heating cycle on that. So it's really, really accurate. You're going down to 0.1 of a micro ohm resolution. So we're really getting into those high levels of accuracy. As we said, test currents up to 200 amps. It's got its own internal cooling system, which is what allows it to actually carry on doing these tests time after time after time. Large 8,000 test memory. And it's actually got this extra function on here, which if you know, is BSG, both sides grounded. So in some applications, you could be measuring conductors that actually are connected to ground, or may potentially have leakage to ground. And in that case, you can actually use a clamp. There's an external clamp that goes on with this, and you can connect that and actually measure the grounding current, and that then gets deducted off the readings. So actually you get an accurate reading in that sort of situation. Again, if you know, it's a specific application for certain things, and it is a feature on, testers of this range. It's nothing much going to go into in great detail this time because it is a bit specific, but it's an excellent feature for those who need it. So just be aware that has got that feature built in. So as you can see there, we've got a great range of micro ohm meters, starting with the 6240, which again is, really popular product, up to the 6255, and then finishing off with a 6292. So whatever you need from a micro ohm meter, one of those products will really fit that bill. And like I say, they are tried and tested in the real world, and we get great feedback for all of these products, like with all the products that we have at Chauvin Arnoux. So just a quick add on to that, we have actually got our data view software. So our data view software can be used to actually create reports and generate, the reports of the data that you've collected using your micro ohm meter. So data view is always a good option there to have a look at when you're using your micro-ohm meters to actually, your stored results, you can then put them into graphs and put them into reports automatically without, a great deal of hassle. So always something to think about. And accessories, we also have a large array of different styles, types, shapes of probes, Kelvin probes, Kelvin clamps, all those sort of things. And we also do bespoke ones as well. So generally, if there's anything else that you want, you want a specifically long one, we have done that for customers who needed, their particular application needed, a longer lead that was available off the shelf. We can actually get those made up for you as well and provide those. So if there, if it's something that you don't see on the website, you don't see in the catalog, don't be afraid to ask. There's always bespoke options where we can actually make these things up for you specifically as well. So always ask, because we've got a lot of stuff available. So that brings us to the end of the webinar today, or the end of the official content, shall we say. So let's just have a summary of what we went through. So we started off with an introduction to low resistance measurement. We talked about resistance, the factors that affect resistance, and we talked about 2-wire measurement and 4-wire measurement, and obviously things like the Kelvin probes as well. We then looked at the factors that affect the accuracy of low resistance measurement. So we went through, quite a few different bits in there about temperature and all those sort of things, contact resistance, lead resistance. We then looked at different applications, so things like buzz bars, switch gear, motor windings, all of those. And then we finished up with a bit of an overview of the Chauvin Arnoux products that we've got available, should you want to get into low resistance measurement. So hopefully you enjoyed the webinar content. It was great to, I enjoyed putting it together and presenting it to you today. So I think it's an interesting subject. I think it's something that most people know a little about, but not a lot. And I think it's something that certainly when I was researching these webinars, I found that the cogs were turned, and I was thinking of more and more applications where these products would be of use. So hopefully it's got the same cogs turning in your head as it did in mine. Okay, so that's brought us to the end of the webinar now. Thank you very much for attending. Remember to download the presentation handouts. So if you go to the go-to toolbar in the handout section there, there'll be a PDF copy of the slides that you can download. You will be sent a certificate of attendance after the session is finished, normally within a few days. And the webinars will be available on demand. So again, within a week or a few days, we'll have the recorded version of this webinar up on our website, and you can find that on the webinar section of our website, www.cauk.tv. That's where we keep all of our webinar content. If you keep an eye out for email notifications, you will see that we have got a new range of webinars coming next quarter. We're just in the process of planning those out and working out what they're going to be. So keep an eye out for that, and we'll send you details of those by email. So thank you very much for attending tonight, and I will now hand over to the live Q&A session.